Hi everyone, good afternoon. This is a presentation on a research work that we are carrying out, which is the CFD dynamic simulation of landslides, to be specific, Chamoli landslide in Uttarakhand. This is a general outline of the topics that I will be speaking in brief in the coming 5 minutes. Starting with landslide, we know that in general, it is a devastating natural disaster which can be defined as the movement of a mass of rock, debris, or earth down a slope. Avalanche, on the other hand, is the movement of large snow volumes down a mountainside. These catastrophes often happen suddenly without any notice, and they cause a lot of destruction and damages, including loss of lives and damage of infrastructures and resources. Now, talking about Chamoli landslide, which is also called Chamoli rock slide, it is a rock ice avalanche. This deadly disaster happened on 7th of February 2021. This rock slide generated a flash flood in various rivers and it dammed local areas and as a result killed many workers at one of the tunnel sites, the Tapovan tunnel site. We can see on the right hand side of the slide a huge volume of rock and ice detached from the steep north face of Ronti Peak and impacted the Ronti Gad. Gad means rivulet here. The avalanche also generated a powerful air blast that flattened about 0.2 kilometers square of forest on the west side of that valley. Researchers have studied the high resolution satellite imageries to find the possible impact of snow dust due to this landslide. However, the mechanism that triggered the flood and the huge amount of water flow in the river is still a challenging question to the scientific community. Now, let me also talk about the landslide simulation. If we discuss about the necessity of such simulations, we can say that they help us to predict the damage that they can that can be caused by a landslide or an avalanche movement. The simulation can help us predict the runout distance of debris. It can help us predict the impact area. So landslide simulation is important and necessary. There are various techniques that can be adopted for simulating a landslide. I'm going to be more aligned with the fluid perspective. Here in the slide, I have listed three different methods that use CFD, that is computational fluid dynamics, for simulating the flow of a landslide. Please note that this is not an exhaustive list for different types of simulation. In the first type, 3D CFD simulation, whole flow domain is considered and divided into small regions called cells. Each cell of the mesh carries value of the fluid property in that region that includes the amount of different fluids, maybe air or water or snow. They include the pressure in the region and so on. Whereas with the second approach, only the surface is considered and is again divided into small regions. Now the 3D surface cells also carry the value of parameters that would signify the fluid that exist above the surface. This approach used thin film assumptions and cannot determine the vertical velocity distribution. The other method uses the combination of direct element method and CFD for landslide simulation. Since in our study we have to visualize the flow of both air and snow in 3D space, we are using the first approach. Going towards the literature review, there is a very rich body of literature that is published regarding the simulation of landslides. I have listed a very few of them in this slide, which highlight the importance of such a study. The existing literature gives an idea about the flow physics. Some of them have done experimental study, others include CFD simulation, but in overall they present the present scenario of landslide simulation. So we defined our main objective as to perform the numerical modeling of rock ice avalanche propagation and its associated air blast. Specifically, we aim to visualize the propagation physics of an avalanche, like the role of temperature, density currents, and rock ice mixture proportions. And the CFD model will be built upon open source CFD framework, OpenFOAM. The flowchart on the slide depicts the methodology that is being followed for the simulation setup. It exclusively includes open source tools and applications. After preparing fluid domain from the geometry data available, the CFD processes are carried out using OpenFOAM and the process is reiterated as required by the results. For the progress of the study, we've developed the geometry using Python script and prepared the mesh for the fluid domain using Snappy Hex Mesh utility, which is a meshing utility of OpenFOAM. The fluid properties are studied and the equivalent fluid models have been defined inside the OpenFOAM case structure. Various fluid models like Bingham fluid model or Herschel-Berkeley fluid model are used to define properties of snow and debris as a fluid, which are actually non-Newtonian fluids. In addition to that, interform and multiphase interform cases are prepared. Interform and multiphase interform are two different fluid solvers in open form. The pictures below show the meshed simulation domain where the lower surface is the terrain. The mesh is dense towards the terrain where boundary layer of flow must be resolved, while the regions of air have a coarser mesh. And what we are doing now is refining the solver setups to obtain clearer results. And also we're trying to prepare case setup for another solver in open form, interthermal phase change form, to capture the phase transition during the flow. And these are the references that are primarily followed during this presentation and study till now. Thank you.